Welcome to this overview of the CAT system developed for the Holy Grail Challenge for CP21. I'm Helmut Simonis. I'm from the Insight Center for Data Analytics in Cork in Ireland. Okay, I should start with a disclaimer. This is not a fair entry for the challenge because I've actually written all the example problems, and so I know exactly what the problems are and what are the specific points that you need to understand in order to acquire these models. But it's still a useful, I think, analysis of what can be achieved with constraint acquisition for these type of problems. The design intent is to be able to find global constraint models that are comparable to hand-built solutions, and using basically the input data and the structure of the data to come up with models that are as good as a human would write. Okay, I should refer to the assistant project. This is basically funding my work on the constraint acquisition side. And I should also mention the work on ModelSeeker by Beldiceanu and myself from CP 2012, which did do a lot of the things that CAT is doing. But CAT is doing a few more things as well. It exploits the structure of the input data in a more systematic way, where ModelSeeker would just take a list of variables. CAT can deal with matrices, it can deal with multiple arguments, it can deal with input data, so it's more flexible in that way. It also generalizes to generic models and not only size-specific models as ModelSeeker did. And the important aspect for the generated models is that they're intended to be executable. So we are generating minisync code that can be run, and that we are running to see whether the models produce solutions. Okay, this is the CAT system architecture. This is perhaps a bit intimidating, but in reality, there are only three aspects there. There is the acquisition of a size-specific model, which is quite similar to what ModelSeeker was doing. Then the generalization of the acquired models to make them size-independent, and then producing working constraint programs from this generic model that we are generating. To explain this, we're going to use a running example of problem type 12, the balanced incomplete block diagram on the instance 0, which is given by 3 input parameters, and a sample solution which is given in the form of a matrix. And so in the first part of the system, we're finding global constraint pattern based on that input data. And for that, we're using a pattern generator that works on the fixed size positive examples and the input data. There are other things going on that we're not really going to talk about, but this pattern generator will help us to find size-specific models. And the patterns involving the matrix, because in our running example, we are given a matrix. Well, we're having things like we're finding a conjunction of constraints for each row of the matrix, or for each column. We're also doing this for blocks and diagonals. We do this for 2 rows of a column, and we can have something like consecutive rows, where we apply a constraint of 2 arguments of 2 lists for consecutive rows of a matrix, or for ordered rows, or for different rows, and the same for columns again. We also have some constraints that work on the matrix or on the transposed matrix. And then there are more cases. We're not requiring them for our running examples, so we're ignoring them for the moment. And here's what we get if we run our example against this pattern generator. We find a sum constraint that applies to each row of the matrix and produces a sum 5. Here we have our example. Okay, we're saying the sum of this row is 5. For every row, it's 5. And we have a constraint for each column where the sum is equal to 3 for every column. And we have a constraint for different rows where we have the scalar product that produces a scalar product of 2. And then we have a constraint that applies to the whole matrix, the Lex chain creator constraint, which is a symmetry breaking constraint. And we have one that applies to the transposed matrix, Lex chain creator as well. But of course, not just this constraint, we would also have a Lex chain creator equal. And in fact, we have many other constraints that we are not needing for our example at the moment. Okay, so this is the size-dependent model where we have these fixed parameters here. Now, if we want to generalize this, we first have to systematically replace these fixed parameters by parameter formulas that tell us how to actually derive them for a generic problem, and then feed that into our generalizer. And the generalizer doesn't do very much. It basically just groups the constraint with the same constraint, the same signature, and the same pattern, but different extra arguments together. And if we find a constraint constraint pattern that occurs in every instance, then this is a generic constraint that we want to keep. Some of the constraints only occur in one or a few of the instances, and therefore they are not generic. We throw them away. And so we get generic conjunctions of constraints. And we now have to be able to compute the extra argument values for these generic constraints for a new instance. And we have to do that with the given data. So this is our generalized model where we still have the sum on all rows, but we now have this symbolic row sum argument. And we have the same for the columns and the scalar product. And we're going to throw away the Lex chain creator because it holds for our running example, but not for all instances, and therefore it's not generic. But the Lex chain creator equal is generic. It holds for every instance, and therefore we retain this. Okay, so now we have to explain the values that occur in our constraints, the fixed values in every instance in terms of the input parameters. And here we have a few of the instances with their input parameters, and we have all the things that are size specific, and we're trying to explain this now. So the domain has range 0, 1. It's the same for every instance, and therefore it doesn't depend on the input parameters. It's fixed. The rows are basically parameter v. The column sum is equal to parameter k, and the scalar product is equal to parameter lambda. For the columns, the number of columns, we actually come up with this formula here, and we are basically producing this formula bottom up using primitive functions like this n pairs, which is x times x minus 1 over 2, or v minus 1 as a primitive function. And we're trying out all combinations of these primitive functions to make them more complex functions. And we find this for columns, and we find a different formula for the row sum. And so now we can explain each and every symbol that we need in our model in terms of the input parameter. And that allows us basically now to run our model for different sizes. If we're given a set of input parameters, we can come up with all the parameters that are needed. We then feed this to the model reduction, and we throw away all the constraints that we don't like. This is following the ModelSeeker. I'm not going to talk about that very much. And then we are producing a working CP program where we are taking the generic model, run this through some code generation that produces both the minisync code and the minisync input data that we can then feed to minisync and the backend solver to generate solutions and see whether these are extra solutions that we haven't seen before. We also have a description generator that produces a natural language description, and all of that feeds into a report generator that produces the overall report that we can look at. This is the generated code. Here we have the data description, and here we have the data file. That's fairly simple because we only have these three parameters here. We are using a little bit of a custom extra program for CAT, which introduces some of the functions like n pairs that are not predefined in Minisync, and some global constraints that are not in the globals list of Minisync either. And we have the variables and the constraints, and then we have the solve satisfy objective that produces a feasible assignment. And this is the generated description. This is text that a human can read, given integer parameters k, lambda, and v, and introducing symbols. Find an assignment for a matrix X with v rows and c of 1 columns, where each element ranges between 0 and 1, such that, and then we have the constraints. And some of the constraints are fairly simple. The sum of each column of X is equal to k, or the sum of each row of X is equal to c of 3, where c of 3 is the formula that we have introduced here. Some of the constraints we are basically not explaining. You have to look them up if you are not familiar with Lex chain creator as a constraint on the matrix. And this is the evaluation that we are getting. We are having our 15 problems of this first stage of the challenge, and we are pretty good at classifying examples. We're getting the positive examples classified 100%, because this is by construction. We're only keeping constraints that satisfy the positive samples. The models are good enough to reject 100% of the negative samples that are given. And that is very encouraging. So when we test it and evaluate it, we actually see that we are reaching 100% of the tests as well. So we are classifying them correctly as either solutions or non-solutions. We generate code for everything, but there are two problems that are remaining. One is for the Golomb ruler, where we are not generalizing the domain bound properly. And therefore, we have the wrong upper bound on the domain, and we are generating a lot of suboptimal solutions, and they are not, well, they satisfy the constraints, but they are not as tight as they could be. For problem 16, we generate solutions, but we're missing one of the constraints, and that means that we have an incomplete model, and we are producing solutions that are rejected by the checker overall, and we're not getting any points for that. So what we have done is a brief description of the CAT system, which was developed for this Holy Grail challenge. Is based on ModelSeeker, but exploits the input structure and the input data in a more systematic way. It can generate generic models, so size-independent models. This is something that ModelSeeker was not able to do. The main difference here is that the patterns are described in a size-independent way and therefore generalize naturally. We generate code and also a natural language description of the model that we produce, and that code can be executed and produces extra solutions for our challenge, and except for two identified problems, it does find the right models capturing all the constraints that were required.